Assalamu alaikum. Dear students, today we will learn the buck boost converter. As the name indicates, it is a DC-DC converter or a switch mode converter that can perform both tasks. That is, it can uh, convert a higher DC voltage to a lower DC voltage, or it can convert a lower DC voltage to a higher DC voltage. Now, what are the assumptions prior to performing analysis of this buck boost converter? So majority of the assumptions are the same that we were assuming in our buck converter or the boost converters that are like the inductor current is continuous, capacitor is large enough to maintain a constant voltage, switches are ideal, switch is closed for the time dt, and it is open for the time 1 minus duty cycle times the time period t, and all the components are ideal. So as shown in figure E and B of 6.11, the boost converter, when the switch is closed, is basically providing an inductor voltage VL equals to Vs, while when the switch is open, inductor voltage VL is equals to the output voltage V out. Now, to understand this thing in more detail, if we can see this figure, what happens that when the switch is closed, we can write KVL as minus Vs plus VL equals to 0. That is the inductor voltage VL is equals to Vs. Now, since the inductor voltage is L di by dt, so we can write di by dt equals to Vs upon L. Similarly, as we did in our buck converter and the boost converter, delta IL is basically replacing DIL and delta T is replacing DT. Now delta IL is basically change in the inductor current. So we will keep it as delta IL, while delta T is basically the time for which this change is basically this change has occurred. So this time was when the switch is closed. So the time for which the switch is closed is dt in our case. So hence we can write delta IL closed equals to Vs dt upon L. So this is the expression for delta IL closed for the buck boost converter, and you already know that after proving the expression of delta IL closed, what we do, we take the switch as open and then we calculate the value of delta IL open. So coming to the next part of this buck boost converter, when the switch is closed, you can see in figure 6.11c that we can now write KVL as minus VL plus V out equals to 0, and hence VL equals to V out. Now, since VL equals to L time di by dt, so we can write di by dt equals to V out upon L. Again, del IL is equals to delta IL, while del T is basically delta T. And since delta T in our case is the time for which the switch was open, so the time for which the switch was open is 1 minus D times the capital T, that is the time period. So hence we can write delta IL open equals to V out into 1 minus D times capital T, that is the time period, whole divided by L. Now we already know that after calculating delta IL open and delta IL close, what we do, we basically sum up these two, we add these two expressions and we take it equal to 0 because the overall change is equals to 0, and hence we get the expression for basically the output voltage. So in the same manner as we did in buck converter and the boost converter, we basically added the two change in currents and we took it equals to 0, and hence we if we make V out the subject of the equation, we get the expression for the buck boost converter output voltage as V out equals to minus Vs time d upon 1 minus t, which is basically equation 6.47. Uh, if we analyze this equation, so one thing is crystal clear that the output voltage is of opposite polarity to the input voltage. But how can we prove that this expression can buck the can basically step down the voltage and step up the voltage as well? So it's very simple. Uh, if basically D is greater than zero point 0.5, then the output voltage must be larger than the input voltage. You can simply plug and play. You can plug in this value of D as say 0 0.6 and you can confirm that the output voltage is more than the input voltage in magnitude. Similarly, if the duty cycle is less than 0 0.5, the output voltage is smaller than the input voltage and hence it will be working as a buck converter. Now, in order to calculate the duty cycle, what we can do, we can rearrange equation 6.47 and can get equation 6.48 for simplification of our working. So if we are to design the buck boost converter or to find the duty cycle, we will use equation 6.48. Or if we are given the input and output voltage and if we are given the input voltage and the duty cycle and we need to calculate the output voltage, we can use equation 6.47. Again, they are saying in the same manner as they said earlier that this expression of equation 6.47 can also be established if we take the inductor voltage equals to 0. So for the switch closed, inductor voltage was Vs into D. For the switch open, it was V out into 1 minus D. This whole expression was basically being multiplied by T. But since we can take T common and put it equals to 0 by bringing it towards the other side equation of the equation, so they simply discarded that T. So in place of Vs into dt, they wrote Vs into D. Similarly, in place of V out into 1 minus D into T, they basically wrote V out into 1 minus D. So nothing to worry about. The concept is the same, that if we take inductor voltage equals to 0, again we can get the same equation as written in equation 6.47. In figure 6.12, what they are giving us is basically the output waveforms of the inductor current and the output inductor voltages. So now, as you already know, that what we will do, we will basically find out the uh, value of inductor current. So for this thing, we can write P out equals to V out square upon R, since PS is Vs into Is. So V out square upon R is equals to Vs upon Is, Vs into Is, since the input power and the output power are equal. Now taking this concept, we can write Is equals to IL into duty cycle. Now from these equations, if we make IL the subject of the equation, we get equation 6.49. And hence we conclude that IL, that is the inductor current, is Vs time the duty cycle whole divided by R into 1 minus T whole square. Now for maximum current, we will add delta IL upon 2 into inductor current IL, and for minimum current we will subtract this delta IL upon 2 from the inductor current, and hence we will get equation 6.50 and equation 6.51. Now for continuous current operation, what we can do, we can take I minimum equals to 0, and hence we can find the expression of the minimum inductance that is required to perform that is required for an operation of continuous conduction mode. So that minimum inductance may be calculated using equation 6.52 or equation 6.53. Similarly, to cope with the output ripple voltages as we did in our buck and the boost converter, we will repeat the same procedure, that delta Q is equals to C times delta V naught, and delta V naught is basically the ripple voltage. And again, uh, we are shown this equation as this figure 6.12, where the area enclosed in the rectangle that is being shaded for you is delta Q. So to calculate delta Q, we will basically calculate this area, and this area will be V naught upon R into dt. So now taking delta V naught as subject of the equation, we can write it like delta V naught, that is ripple voltage, is equals to V out into D upon RCF. Now to basically have a percentage ripple concept, we will basically write delta V naught upon V. V naught is equals to D upon RCF. So this equation 6.54 is basically representing the percentage ripple of the buck boost converter. Finally, as we always do, to basically calculate the ripple voltages due to the equivalent series resistance. So for this, the equation is the same. That is delta V naught ESR is equals to delta IC into RC, where delta IC into RC can be written as IL maximum into RC. So using this equation 6.55, we can calculate the ripple voltage that is the dominant ripple voltage, that is due to the equivalent series resistance ripple voltage. Now coming to some numericals of buck boost converter. So they are saying that in the buck boost converter, the supply voltage is 24 volt, the duty cycle is 0.4, resistance, the load resistance is 5, inductance is 20 microhenry, capacitance is 80 microfarad, and the frequency is assumed to be 100 kilohertz. So we need to determine the output voltage, the inductor current, average, maximum, and the minimum values, and the output ripple voltages. So first of all, we should consider that the duty cycle is less than 0.5. So if the duty cycle is less than 0.5, the output voltage must be lower than the input voltage. So as we put in the values in equation 6.47, we easily calculated that the output voltage is 16 volts in magnitude, which is less than 24 volts. That is the supply voltage of the buck boost converter. So as discussed earlier, that whenever the duty cycle will be less than 0.5, there will be a buck converter, and whenever the duty cycle will be more than 0.5, it will be a boost converter. Now to calculate the inductor current, we will use equation 6.49 and 6.51. So from 6.49, it is VSD upon R into 1 minus D whole square. So Vs is 24, duty cycle is 0.4, R is 5 ohms. So hence we calculated that the inductor current is 5.33 ampere. Now for delta IL, it is Vs dt upon L. So it is 4.8 ampere. Now we know that delta IL maximum is basically IL plus delta IL by 2. So IL maximum is 7.33 ampere. And similarly, IL minimum is IL minus delta IL upon 2. So it is 2.93 ampere. Now for the continuous current or continuous conduction mode, I minimum must be greater than 0. So using this, we basically already concluded that the delta V naught upon V naught is basically D upon RCF for constant output voltage or for a nominal ripple voltages. So for that purpose, we already know the D, we are given basically RC and F. Hence, we calculated that the percentage ripples are almost 1%. So that is all from my side for the buck boost converter. So the conclusion is that a buck boost converter is capable of performing both tasks. That is, it can boost the voltage up, it can drop the voltage down. It can basically provide a an output voltage that is of negative polarity. If the duty cycle is greater than 0.5, the output voltage will be boosted. And if the duty cycle is less than 0.5, the output voltage will be less than the input voltage. So inshallah, in the next lecture, we will study the Kirk converter, the SAPIC converter, and some of the things that are related to the DC power supplies. Till then, take care and Allah Hafiz.